All right, so this is the primary interview process. The purpose of this interview is to check all the subsystem teams, make sure they're on par with their research, and detect any holes in the model-based design timeline and identify the technology readiness levels. Today we're with the experiment team led by Reese. Reese? Reese, you muted yourself. Reese, you're muted.
Oh, there we go. Sorry, I lagged a little bit when I clicked that. So yeah, today I'm going to be talking about the experiment team and the progress that we've made so far, and give a brief overview about all the different components. So to start with, it's important to identify the three different components that comprise this team, and the first of which being managing the onboard payload and experiment. The second responsibility of this team is doing simulations and validating design decisions. And the third component of our team is doing orbital dynamic verification and predictions. And so within these three components, there's a couple different aspects I want to discuss. The first is the design challenges associated with each aspect of the team. So for the payload, there's a couple of considerations we need to think about. We need to think about how the optics are going to behave. We need to think about thermal considerations, photon tolerances, radiation shielding, and power management. And these are all incredibly important issues when you're doing any onboard experiment that's got any form of camera on it. And so I'll go down this list and explain each one. So for the optics, we need to really understand the dynamics of how it's going to behave in space, because we need to be oriented at a certain point in space to observe, and making sure that it's fixed on that point for long enough such that we can get adequate data and transmit that back down to the ground. The second thing we need to consider is thermal considerations. So some cameras have tolerances in how much heat they can absorb before they overheat, and that will cause issues with getting that data, and so that's something we need to account for. Photon tolerance is basically, because light is all based on photons, we need to make sure that we have the adequate number of photons to generate a high enough resolution image, and that goes back to the idea of making sure we're fixed on the correct point in space and absorbing all that light that's necessary. The fourth component is radiation shielding, which is a really, really important topic for cameras. Basically, the lenses and the various aspects of the camera are susceptible to radiation, and this is an effect that has been observed on the International Space Station. It can cause pixels to go dead and lose data, and that can cause a lot of issues when that's our primary objective. So we need to make sure that we're avoiding high radiation zones or doing as much as we can to mitigate any radiation directly hitting sensitive components. And the final aspect is power management. When we're doing the observations using the camera system, we need to make sure that we've got adequate power at that point in time in order to perform the observation for the required period of time. So those are the considerations that we have to do for the onboard payload. The second set of design challenges comes with the simulations and testing. And so there's a couple things that we need to consider. The first is launch vibrations and perturbation tolerances. And so during launch, it's a high vibration, high intensity aspect that we need to focus on, and depending on the payload service provider, the launch provider, they have a payload user guide that specifies the expected vibrations at each phase during launch. The second thing that we need to help consider is the satellite thermal situations, and so this is for the entire satellite, making sure that no zone of the satellite will ever be exposed to too much heat or heat gradient or lack of heat, to make sure everything performs optimally, because onboard power systems will be dependent, their efficiency will be dependent on thermal considerations. And then the final thing that we need to do as for simulation and testing is work with control system responses. So when we are telling the satellite to perform a maneuver or reorient itself, we need to be able to validate beforehand what the expected maneuver will do and what the state of the satellite should be afterwards. And so that's an incredibly important consideration. And so those are the simulations and testings design challenges. And then dynamics. So we also need to consider a lot of orbital dynamics for communications and keeping track of the satellite. So the first thing we're going to be responsible for is the ground station timing predictions. In collaboration with the ground station team, we should be able to do predictions about the state of the satellite based on two bits of data, basically. If we know the position of the satellite along the orbit on two separate times that we can time when it's over the same ground station, we can determine the velocity of that component and use that to verify the orbital elements and get very accurate predictions on how the orbit is changing over time. And this goes into the telemetry feedback loop. So with the telemetry feedback loop, what this is going to be doing is it's a sort of harmonious relationship where the satellite will communicate to the ground its current telemetry, and we can use that to predict future positions and orientations of the satellite. And then when we plan a maneuver, feed that back to the satellite, and then get the new data back down. That way we can say where the satellite is currently. We get that information. We can then plan any maneuvers or reorientations, command the satellite to do that maneuver, and then validate that that maneuver performed as expected. We also, in terms of orbital dynamics, going to be doing onboard power state estimations. And so this is basically using the fact that we're using solar energy to power the satellite. We need to be able to determine optimal positioning in order to generate enough power to perform whatever upcoming commands are going to be performed on the satellite and make sure it's always got adequate power. The fourth thing we need to consider is orbital degeneration. So over time, due to solar radiation and atmospheric drag and a couple other factors, the orbit will be degenerating over time. And if we don't account for this, we won't have an accurate prediction of where the satellite is on the point in space, and therefore the maneuvers that we command it to do wouldn't be accurate. And so it's important to consider how that orbit's going to degenerate over time. And then the final thing is the Van Allen radiation avoidance. So there's high radiation zones where high energy protons and electrons get stuck in the Earth's magnetic field and create these bands of high level radiation, which is incredibly dangerous for satellites and humans. And I touched a little bit on that before with the payload. It can completely fry onboard systems. It can cause the camera to lose information. It can cause communication blackouts. It can cause a lot of issues, and so we need to be doing as much active avoidance when we're picking initial orbits and doing maneuvers that we're not going to be spending too much time in any of the Allen radiation belts. So those are the design challenges that sort of encompass the team. So those are categorized into the payload, the simulations, and the dynamics. And so the critical components in order to deal with these various challenges are representation of the satellite as a dynamics model. Once we have that, we can do various vibrations analysis to verify how the satellite will behave during various events. We need to have an orbital simulation available for the satellite, and we need a discrete model of the satellite hardware. That way we can do thermodynamic considerations using either finite element analysis tools or other miscellaneous tools. And so the solutions for these problems, so for the thermodynamic considerations, the two pieces of software that I've come across are called ThermoCalc and ANSYS FEA, which stands for finite element analysis. These are two tools that are frequently used for doing analysis of structures and thermal considerations, and so we can use that to gain an accurate representation of how the satellite will behave when subject to various considerations in different parts of the orbit, so we can verify how hot will the satellite be or how cold will it be at different points in the orbit when it's exposed to different amounts of sunlight. The method we'll be using for making the vibrations and modeling those is called the Laplace transfer function approach. And so once we have a model of the satellite built, we can subject it to various vibrations down on the ground before we launch it, and use this to determine the transfer function using the Laplace method. And once we have the transfer function, we can predict all of the dampening elements, spring elements, etc. of the satellite. And once we have that, we will have a model of how the satellite will behave under various vibration circumstances. When we have that model, then we can use the payload user guides for whatever launch provider we're using to validate that it will meet all the criteria that's required. And then the final solution is going to be an in-house simulation for orbital dynamics, or using the software called FreeFlyer. I'm investigating both of them currently. In terms of the in-house solution, I've currently got a orbital dynamics simulation working where we can observe the location at 2 different times, and from that extrapolate the velocity to determine orbital elements. And this has been tested at a high scale, and so I believe this will, with adaptation, work with the information provided back down from the satellite in order to determine accurate orbital elements. And so I wanted to really open everything up to questions near the end, because I know that was a lot of different content and a lot of different aspects. So I wanted to make sure I spent the most time addressing what you guys think is important issues.
Yeah, so 2 things come to mind. The first one is definitely look into AGI. We just got the licensing for that, and that's probably going to be your best bet for doing the orbital analysis, because that's simulation, that's software, that's data analysis and data handling at any point in time in any kind of orbit we put it in. So maybe compare those 2 and see which one's going to be better, but we should be getting that by, if not today, tomorrow, Monday.
Awesome. Yeah, that definitely sounds awesome.
Yeah, so definitely look into that software, because we already have the licensing for it and everything. The second thing too is, can you touch on how we're going to conduct these tests in-house? Obviously, software testing is okay because we can just take a .mdl file from, the structures team, put it into a testing software and get some data back. But, when we start getting the hardware, how are we going to do like thermal vacuum testing at different temperatures for the thermal cycling? We also have a sinusoidal vibration testing, and all of these has very specific requirements that we have to do. How are we going to do that in-house?
Yeah, definitely. So I'll touch on the vibrations element first. So the method that I discussed, the Laplace transfer function, is basically a method for identifying an analytical solution to the vibration for the system. So once we have that analytical solution, we basically, to obtain that, we subject the satellite to, for example, a sinusoidal vibration and study the response. And if you have a couple of key observed characteristics of the response, such as the frequency and amplitudes, we can feed that into the transverse function and use it inverse Laplace to determine the analytical solution of the vibration. Once we have that analytical solution, it will tell us the damping elements, the spring elements, and the mass of the satellite in terms of this dynamics model. Once we have that dynamics model, then you can subject it to any vibration that you can think of and analytically solve it, or use a software to solve it. Both work equally.
That's the software side of it, but what about the hardware side of it? Because, I mean, you look at, like, for example, I'm using Endurosat as my reference point, but you can also use Cal Poly. They're using software given to them by, like Northrop Grumman or NASA themselves. How are we going to be able to replicate the exact same testing at FAU?
Oh, it's the beauty of the transfer function approach is that we don't have to subject it to all those conditions that are going to be it's going to be exposed to during launch. Once we have the analytical solution, we can substitute in any forcing function to solve. So when we have the payload users guide, it has the vibration frequencies and basically forces that are going to be acting on the satellite. Once you have the transfer function approach done and reversed it backward, you can plug in any force. So we can work with those forces and gain an accurate representation of how it will behave during those different phases of launch. The thing I'm currently working on is making sure that we can get precise enough measurements from when we're doing the physical testing with the, for example, sinusoidal vibrations, that we can get accurate predictions and validation. So that's something I'm currently looking into. I was primarily more focused on the approach, how it's going to work, and how we can feed that into all the other systems. So I'd definitely say the thing that we need to focus on right now is how we're going to obtain accurate enough measurements when we're doing the sinusoidal.
Right, and I definitely think the approach is perfect. It's just that execution piece I'm a little worried about, because do we need to buy hardware to actually execute the software, or for the sinusoidal vibration, do we need to buy a piece of equipment that can actually execute a vibration test? Because I don't know what is it that we're going to be using to actually execute the software and the coding that you're talking about. That's a piece that I'm a little worried about. I don't know how much each piece
Yeah,
of
so
equipment
most of this will be done physically. We'll use the actual physical model of the satellite. So I've seen in a couple different universities and teams, they build two models. They build one model of the satellite for doing testing on ground, and then once they've made sure everything is great with that model and subjected it to the testing, they build a fresh model, which is the one that would be actually launched into space. So when we have that testing model of the satellite, or an adequate testing model, I know one of the critical components of hardware is basically a damping table. So it's a special table. I believe we might be able to get access to one independently. If not, I do know that there are ways to construct them. It is quite difficult. So I think we should go with the approach of finding somewhere else that has one of these special tables. And what this table does is it removes all outside vibrations, basically, from the system. And that's the most important consideration when doing this physical testing, is you don't want the ground vibrations to be picked up or anything like that. Now, this is typically more important when you're doing, high-level laser physics and all that sort of stuff, and looking at photons of individual particles and making sure they're behaving as expected. We should be able to just use something comparable just to remove external vibrations when we're doing the study. Then you'd subject it to the sinusoidal vibration physically. So you take the physical model and subject it to the sinusoidal vibration with there's devices that can basically vibrate in certain conditions. They use similar things in a chemistry lab for stirring solutions, where you can basically put something on the machine and use various controls with the machine to produce certain vibrations, and then you measure the response given that vibration. That's how you would get the analytical the transfer function in order to work it backward and find the analytical model. So I definitely think the two things that are currently unknowns are the how much damping we will need. So what level of accuracy will we need in terms of doing our vibrations to make sure it meets the thresholds that are specified in the payload user guide, and finding adequate hardware to produce these known and easy to work with vibrations, such as a sinusoidal vibration, and making sure we can measure the responses of that accurately. I definitely think that is something that we need to look more into.
Something I would suggest is, if you look up Endurosat and also Cal Poly, they actually offer services for you to send your CubeSat to them, and they run the testing for you. So it might behoove you to go and contact them and then start calculating costs before the September interviews to see which one is going to be a more cost-effective solution, because we're as soon as we get qualified, I think in the next week or 2 weeks for 501c3, we're going to be asking people for to help us pay for this. So we have to have accurate cost estimates for how much this satellite's going to cost. And this one kind of makes me raise an eyebrow, because it's like, well, if we do it in-house, we need to have an equipment list for everything and time to build it all before we get there, because we don't want to have to build the equipment and then test it. We want to have the equipment ready to go to test. And it might be more cost efficient for time cost and money-wise to actually just send it off to like Cal Poly and have them run the testing for it and then give us results back. So if you can,
I definitely think that's the approach to go with it. Given that they definitely have more experience with this stuff, and it would be our first time conducting these vibrations analysis, we would definitely want someone who's got a bit more experience to make sure we have valid data for that, because the vibrations are incredibly important during launch and making sure the satellite can handle those.
Okay, so that leads me to my next question then. For hardware in the loop testing, when we start getting the components and the kind of disassembled subsystems, do you have any idea on how we can be able to test the hardware within a software? So like, I don't know, like you have a mouse connected to your computer and you want to run testing on the mouse using your computer, and you kind of plug it in. Do you have any idea on how we can test certain reaction wheel data inputs that we give it? It's later in the process of the model-based design timeline, but that's definitely something where your team is going to come in and start saying like, okay, give me your microcontroller and I'll run some tests on it and give it back to you on its performance levels, or give me your ADCS system and I'll plug it in and I'll run some testing and give you the slew rates back to you. Do you have any idea on how we can start executing that kind of testing?
Yeah, definitely. So, in terms of the reaction wheel, since that's a specific example, I'll work with that. So, the way we want to handle that is we want to basically model the physical system and just use physics to basically do all the predictions. So, if you have the mass of the wheel and you know the RPM of the motor that's going to be spinning it, we can work and calculate how much torque that would produce on the vehicle or the satellite. So that's the first step, would be to identify the ideal conditions. Basically, we're using this mass and this motor, we should be able to produce this much torque. Then the second, so that's the idealized case. And the second way we're going to have to do this is you can put sensors. A lot of them, I think, actually included with some of the components for the reaction wheels that will actually give the current readout of the torque. And then we would want to physically weigh the wheel. So when we get the wheel machined or purchased, we're going to have to weigh that using just a standard scale, something with high precision, so we can get a full-blown accurate weight and again accurate calculation of the RPM. And then you do a similar approach of using those values now rather than the idealized case of this is because when you purchase the motor, it should have a maximum minimum RPM that it can be spun at, but in actuality that might be slightly different. And so that's how we validate that component. If we do that for all three wheels, we should be able to determine all the torques that we can produce on the vehicle. And then when we have the mass of the entire system, we should be able to determine its inertia and thus how it will respond when we spin up the wheels. So I'm a little less concerned about that aspect of things. The primary component of validating that will basically be just testing testing the various components and making sure that the values that we get are accurate. I do believe there are other ways we could validate that it's working as expected. I think it would primarily be using physical models, though. So, for example, you might want to isolate the system, like, for example, hanging it using cables or strings or anything, and spin up the physical wheels to make sure that the torques that are being placed on it are indeed what we predicted them to be. So I think that would be mainly doing computations in terms of calculating performance and what we expect, and then comparing that to a physical test where we isolate the system and spin the wheels with all the other components on board to verify that it works.
And the reason I asked that is because it's not me asking it, it's NASA. In the proposal, they specifically request that a feasibility review be conducted. There's a merit and feasibility review. The merit review does not concern you. The feasibility review is really where your team comes in, because NASA wants to see the probability of success. They actually want a percentage of the probability of success of not only the mission, but all the individual components along the way in the testing process. So right now, we're going to get AGI, and the teams are going to conduct software in the loop testing, right? They're just going to use AGI and use, the different scenarios. Okay, that's no big deal. But when we come to that later timeline in, like September and October, when we actually need to start testing pieces of equipment, we have to give graphs to NASA and give probabilities of success for each individual component, as well as the satellite in its entirety. And then that has to be reviewed by an external committee that's not associated with the project. So, finding ways that we can test that in a way that you think will be beneficial for us as a team to demonstrate that our satellite's actually going to work is definitely going to be something that you'll have to, and your team will have to, analyze throughout the coming month and a half when we actually start getting to that point. That's a big one. That is they actually give a percentage of how much that's weighted on, kind of like our SAT test. I believe it's 60% is a feasibility review. Our feasibility review is 30%. So the relevance to NASA is 40%. The merit review is 30%, and the feasibility review is 30%. So that's a bit, and that's the three categories they weight, and they weight out of like 100 or something like that. So if we need to get a high score on that feasibility review to say like, hey, our satellite's never flown, but it's going to, and that's definitely where that's going to come in. So I would say look into that, and then look into costs, because we got to assess how much this subsystem is actually going to cost, and whether it's more beneficial to send it off or actually do it in house, because you're pretty smart. I'm sure you guys will probably be able to find a way to do it in house. That cost piece just comes into play.
I definitely think in terms of making sure that we can prove to NASA that we are doing everything properly and that it would succeed, I do think it's probably in our best interest to send it off when possible for external testing just to validate everything. Because if they see Caltech or Cal Poly or any one of those guys who already provided testing services to other satellites, if they give us a good go-ahead and they give us some good information, we use that information, they can have a high degree of confidence that that information is correct. So yeah, I definitely think that's the approach we'd want to go with. For some of the other considerations when we're doing the testing, we need a more complete system. So for example, I'll take it back to the torque. When we're computing the torque from the vehicle, we'll need to know the center of mass and the center of gravity of the vehicle, and so the satellite. And so in order to do this, we've got sort of two ways of approaching it. We can do a mathematical model where we look at each component and the mass distribution along those components and use those to analytically predict where the center of mass would be and therefore where the torques would be acting. Or we can then, once we have a physical model, we can hang it basically like a pendulum in two different positions. And when you hang a mass or a rigid body from a couple different positions, you can very, very accurately determine where the center of mass of that is. And so we can use that to validate those models. So I think a lot of the testing is really going to come down to mathematically and physically modeling various systems and then performing physical small-scale experiments to validate that information. So I think, for example, like I said, the center of mass is a big one. The vibrations is another big thing. In terms of thermal, most of the research that I've done, the software that handles a lot of that. So we basically would give it the models of the satellite and subject it to different conditions, and you would see how the heat would distribute across the system. And so we're going to want to, when we do that aspect of stuff, we're going to want to validate that against the thermal baking, which can be provided by NASA and other providers. So it's really coming. What's the timeline of things basically is we get this other information from the other teams, perform this software testing, for example, thermal considerations. If we get any red flags at that stage, we know we have to redesign some components or move some stuff around. Once we get into a place where the thermal testing is saying we're all good to go, that's when we would proceed with sending off the satellite to a thermal chamber, a vacuum chamber to bake it, and look at the data that they give us. And if we do those steps, I think NASA will, with a high degree of confidence, say that it will succeed within that area, because we can provide a mathematical and physical model of the system. We can validate that with software testing, and then we can further validate it with physical testing of a CubeSat model.
Okay, that sounds good. So I kind of want to shift gears a little bit. Can you talk about the components list for the library? I just haven't seen it yet. I was wondering if you have, like, if you could just look something up and show us and talk to us a little bit about what that setup's going to look like.
Yeah, so I didn't include that in this presentation, but I can talk about it.
I know you didn't. I just, we have some extra time, and I figured we'd talk about it now because that's something the library is going to be looking at, and that's going to help the ground station team out because they can't put their antenna on top of the library until we give them this. And on August 4th, we're having an interview with COSO to get $1,000 for this thing. So I just want to know if you can, if it takes some time to look it up, it's no big deal. But I just want to know if you can present that.
Yeah. So the sort of primary elements are some form of computing element and a display element. Those are the two ways you sort of, from a high level, you have to look at things. And then so for a computing element, we should be able to use a very low power computer, such as a Raspberry Pi, to run the software, because we can cycle through images, we can cycle through web pages, and rather than running any simulations on board, we can have a recording of said simulation being run on a more high-performing computer, such as my laptop, and take a screen recording of that and have the Raspberry Pi replay that video. So we're not having to do those expensive simulations on a tiny little computer. So that's why we can go with such a low-cost option, such as a Raspberry Pi, which are typically on the range from $20 to $40, depending on various sites. And so that's the first aspect of it handled that will basically be responsible for doing all of the logic within the library system. The second thing that we need is some form of input and output system. So you've got a couple options with this, and I think there's definitely a most elegant solution. So when it comes to hooking everything up, we have to output what it's doing, so some form of a screen, and we need to have some way of interfacing with an input that we can use to control or change things down the line. Or if we wanted to make it interactive down the line, that would be required for that too. And so the way of doing that is you could use an external monitor and keyboard and mouse. And I don't think that's very elegant. I don't think it looks cool. I don't think it's easy. I think there's better solutions out there. And so one of the things I've come across is there are touch screen displays that natively can work with the Raspberry Pi that come in these enclosures. So basically the small Pi goes behind it, and then you have this nice display, and you can interface with it via touch. Those range from $70 to about $100. And so that would handle pretty much the entire hardware side of things for displaying data and displaying cool things and allowing people to interact with that. And so this would be a very small thing. It would be around the size of an iPad total. So it's the screen of the size of the screen is similar to an iPad, and basically a tiny Raspberry Pi behind it that you can see. And so it's this. It comes in a nice enclosure. And so the next question is, well, what do we do with that? And we're going to want to mount that to something where we can display physical models of hardware. And I think that's basically the area where choices on cost are going to matter the most. So you could go to Home Depot, pick up some wood and stain it, and pick up some plexiglass and make like a nice enclosure where the base is just like a wooden box, and then you have like a plexiglass box on top of it, and then you mount the display to that. And so you would have this sort of almost like a rectangular looking device where it's more going upward, more like a rectangular soda can, where the base of it would be wood and could store power cables or anything like that we need to route to the computing system. And then we could put shelves in it with plexiglass, and on each shelf display various components. So you could display models of the CubeSat, you could put graphs, anything that you want.
Okay, I like the idea. We just need to present that on the 4th. So, and we have a cap of $1,000. So I think that, I remember we were talking about this the other day about how you were going for a more cost-effective solution. I'm pretty sure that if we're able to make this a nice-looking thing, that COSO would probably give us around, $400 to $600. I know, so 200 of it is going to go to a tablecloth, but I mean that's going to leave you about $300 to $400, potentially $500 for this setup. So,
since the computer is only about $100 cost, that proposed model of building it in plexiglass and stuff, I think we should actually not go with that option. I think we can purchase a display unit to have everything in it, and that costs us maybe $100, $200.
Can you look that up, what that looks like? Can you look up like an image of what that looks like?
Yeah.
Maybe like a pretty good one. I used to like shelves or units.
Something like this. And we could mount with a highlight. You can even mount the physical display anywhere almost, because there's Raspberry Pi and closure. So that's very high display closure. Sorry, I'm talking about that.
Okay, so that would be, you said that would be like in front of the freestanding display case?
Yeah, so we'd mount that somewhere on the display case, because that has everything connected, and then you just need to run a single wire. So here's a review of another example on the back, where all of the outputs will be routed through it. So we have a really nice looking mount on the display. So you could build something like that, sort of where you could go and buy wood plexiglass and build a very similar thing, but anything like this would work.
Does that have shelves?
That's probably way too big for what we're looking for.
That is quite
those are definitely a bit more expensive for hobbyists, right? You can get them, I think some of them use glass, and we don't really need glass. I think you gotta go with something like plastic or plexiglass. But I think you can get one of these on the order of $400, so I know these are more expensive.
Okay, if you can find one and then just provide us like the link or an image of it, so that, and then that way when they give us the money, they actually are the ones that go through with the purchase. So we just kind of tell them what we need. So if you can find that and find the link for it and find everything you need, get it in like a Word document list so we can send it to them, or we can present it to them, I should say, on the 4th. That would be great. So you mentioned doing a screen recording of a software simulation so that it's not run on Raspberry Pi. AGI software actually lets you do a video recording of a system setup that you want to do, whatever you want to record. So if we want to, let's say, set up a ground station with a radio frequency dome, and then showing the satellite flying through that dome, we can record that. If we wanted to record the satellite in low Earth orbit, expanding solar panels or whatever, or reorienting itself, like, we can record that in the AGI software so long as we make it in the simulation and click record. And then that way you might be able to take that, I think it's an MP4, which is great. You can take that and put that on the Raspberry Pi.
Just real quick, I just know this is going on YouTube, but this is obviously showing off myself and talking about this code stuff, but I don't want them to sort of see some of the noises and some of the thought process. I don't think we're necessarily going for something that would be more sensible. We could go for small like showing the stuff and talking a bit more casually. That's what I would do.
Right. Yeah. No. I mean, it's whatever you. I mean, yeah. There's obviously a balance between being nicely cost effective and also reaching a nice display case. So, whatever you find that balance, just send it our way, because we do have to present on the 4th.
What price do you think will be that seems to be the big determining factor? For example, with this one is $250. I think that would be an adequate start, but depending on how many components you want to put in.
Yeah, I mean, honestly, if you want to do something like, a 4-foot tall, piece, like the wood kind of 4-foot tall stand that you were talking about, and then the iPad is like slanted 45 degrees on that, and there's like a little, then it kind of extends back a little bit, and there's a plexiglass box with like a stanchion type thing, and then like a model CubeSat. We get one of these 3D printed, and then that kind of sits on in there with a little, like a little something that has something written about the CubeSat size and a little description.
Yeah, definitely. I think we should look at these. I think based on what information, we should go less of shelf space than them. Because I don't know how much we're going to be looking for. I think something more of this would look really good. Where I can't remember it's on top. We can use some LEDs in the bottom as well. Of the display that's going to shine up with the sat. That way we can really focus on just a couple things like the sat. Having a bigger, because if we have these and we don't pull up every shelf, it'll look pretty bad. Whereas if we have something more similar to this, the attention is really drawn to the element. And this, which is, I think, why they typically use drawer and that sort of stuff. So, yeah, so on this exact setup, you can see my cursor.
Yeah, we can.
Mounting the display where my cursor would be, having things CubeSat on the and run these along the inside. I think they look really slick, and so that was $279 to buy. With the display, $150. We have the LEDs, $20. So we're $400 for it to go, $450. And all the components on that.
And I mean, honestly, if you think it's a more cost-effective solution to spend more money on the case and less money on the touchscreen, and maybe you can get something that's just a display screen, and we have it just sequentially run through certain videos, that could be maybe something you want to consider too. Because if the case is more important to actually hold everything, then we might just do you could just do a screen.
Right. The only sort of reservation I have with that is making sure that it's mountable in a very nice, easy way. A lot of these displays have like mounting solutions where it doesn't look messy. So it'd be a shame to get a nice looking case and it's not a really messy look where it looks like we just strapped up a computer monitor to it. So let's just very quickly. So I mean, this is just the case with the LCD, and it's not $20. So the cases aren't that expensive. If we start looking into the touchscreen, that's when it adds like $50. So if we were to go with, for example, a model like this where it is just the LCD, we would have to have some method of plugging in a keyboard and mouse and one interface with it is the only downside. But I think it's doable as well if we're not planning on doing much with it. The reason I was thinking that we could go with a touchscreen is down the line if we have any interactable elements where people could maybe browse different simulations and go from the previous to the next, see photos that we've uploaded. The touchscreen would really provide a nice interface for people to do that.
Okay. Well, that sounds good. I don't know, Diego, Stefano, if you have any comments or questions or concerns.
Are you working closely with the actual experiment board that's OAM that you can start? Are you doing anything of that specific?
Sorry, I'm just these questions.
So the experiment board, like the OAM for instance, are you? Did I see much of that presentation? Are you focused on that? Are you working on
information about that currently, which is why that wasn't included in the presentation aspect. I know the very general ideas of it and how optics work, and that's why I tended to focus more on the optics in the lenses. I don't have too much information actually about the specific experiment being performed. That's why I was more focused on general optics and general camera considerations.
Okay.
Because the radiation belt is the end be all. If you see, I think I just saw an image on Twitter this morning from Bob and Bulldog, who was the MT crew. They had a picture taken, and there was no sort of spots on the camera they used where information was missing. Because of radiation hitting my camera while I was in the ISS, and the ISS generally avoiding high radiation zones. The Van Allen is basically a really important thing to consider, and it is basically a zone of radiation where if you don't have any shielding, it would be absolutely lethal to satellite like us. And I think you're looking on the order
low Earth orbit
without
as well?
any shielding, 300, 400 grams. I believe it is. Don't go wrong now, but it's high dose radiation, and so the way that analysis is okay is this spacecraft provides a lot of shielding, and they do a lot of these concerns of the satellite. They actively try to avoid these zones. So you put your satellite on these zones mistakenly for an extended period of time. It will fry a lot of the onboard components. So it's a really important consideration. Picture what it does. I think I just saved it in my phone, so I'm going to pull it a little quick.
That is an issue in low Earth orbit. I mean, I get at the upper and lower latitudes where it actually goes back into Earth. That makes sense. But in low Earth orbit, I mean, a lot of that looks like.
It's actually the thing that's known as around Pluto. There's actually a zone that they specifically tell people to avoid. It's near the equator near South America, I believe. I'm not sure to find one.
Right now.
Yeah, there's like a bunch of different zones. I think this is
right between there and the dangerous spot. There's a small area there.
Yeah, it's because it follows the magnetic process.
Right there, you see that? Up a little bit, up and left.
Sorry.
Down.
That was actually the image I was looking for. That's that zone, for example, you do not want Lasso and they actively, satellites are active avoidance of that area because it's high radiation, and so there's a lot of considerations you have to do with regards to the satellite, which is why I was rolling in the Orbital Dynamics and the team's responsibility, because to the right of this image.
Yes, that one.
Yeah.
Is that what we're worried about right there?
So this
inner cylinder, or not cylinder.
Yes, there's multiple sort of zones within it, and it follows the magnetic field lines of the Earth. It follows these lines of the Earth. If you actually see it, the lines are very, very close because high energy photons, electrons, stuff that can go back and forth because they are They're traveling and have momentum that's propelled by these feel like, but when they get very close to the Earth, the magma pushes them back away, and they follow these lines perfectly, and that's why I had that donut shape. These are the two regions in which you don't have a lot of radiation at the poles, because the way the magnetic field lines are oriented, you wouldn't trap them in loops. Whereas if you're in the northern and southern latitudes, you would be avoiding those. And so I know there's regions of higher density that we have to avoid, and that's going to be very, very important because it absolutely fries satellites. I'm just going to share this photo from my phone real quick. Airdrop this.
So, Diego, that's the kind of anodized shielding we're talking about? The anodized shielding on the aluminum, does that stop this kind of radiation?
I should say that's
Or is that just corrosion?
They do both. The shielding can mitigate it and never properly take it away. So you can reduce it to a small level of a tiny International Space Station. They still are subject to a lot of radiation because of all the shielding that they have. The small satellite will be subject to that. So on this image, all these offsets that you see on the image, like here, where all the arrows are pointing, all these results are where the camera has been damaged from the radiation, and so this is a camera that's sitting inside the International Space Station. And so if we don't make sure to consider the radiation effects that could happen on the experiment, this could happen to the onboard experiment and ruin some of the data.
So those are LCD pixels that are actually, I mean, like individual LCD pockets, I guess, inside the camera that are broken?
Right. So this is a picture of a local data point. You can see all of these little zones on the camera sitting on all the ISS, which is shielding the camera. This camera was never exposed to the academic space and didn't have any shielding. So and then you see all these spots everywhere that would cause issues with data. If we invalidate any data within that zone. So there's a ton of them. So that's something that we're doing research on. So it's quite a difficult phenomenon to understand. The shielding is definitely the biggest thing that comes into the basic way to think about it is high energy protons and electrons hitting satellite would cause radiation and transfer energy. And that energy, when transferred, the water systems just don't handle it. And it causes ripple effects. So yeah, if you were like naked in orbit and just floating around, I think you would die within 8 hours. I mean, like most days, or nothing. It's a lot of radiation. So yeah, there's the numbers.
Real quick, and then we gotta hop on. We gotta go to the ground station.
Yes, this is measured in mega electron volts per cubic per centimeter per second. So it's not an inconsequential amount of energy that gets transferred to the satellite. Yeah. Do you have any other questions? Sorry, I know I went on a little bit about this piece of research and it seems to be very, very important.
No, I think that includes it. I mean, I think you're on track. Like, you know, the testing that needs to be done, and it's just look into that kind of conducting the hardware testing based on standards that are needed per team, and then get us that list for the library, and that should be good. The library is more important right now because that's due on the 4th, but you have about until early September to kind of figure out how to do, reputable testing before we go and sending off the whole entire satellite.
Right. I'll be able to start allocating more time on that. Starting next week, I have 5 finals over the next 7 days. So I've got quite a bit of stuff to get done. So after that, I have 2 weeks where I'm completely free before even my classes start. I can get you a solid list of everything down. But for the next week or so, I'll probably be focused on my exams and stuff like that.
Wait, so you can't get the list by the 4th?
I could probably get the list by the 4th.
Okay. All right.
I'll make sure to make that priority, because I have already a good idea of the list, but in terms of like any in-depth analysis or anything else, sort of stuff, or, you know, getting the procedure written out and how we're going to do everything, it might take me a little bit more time to actually get it all open. As long as the biggest thing is what you guys think we should do about the display, and whether we're going to go with the touchscreen or just the LCD.
Okay. I mean, we're on board. We're on board for the 90%. So whatever, you know, you make that final call for what do you think is going to be beneficial for us to, you know, earn some standing with the library. We'll leave that up to you.
Yeah. Do we have any or like decals of the logo? Because I was thinking with a lot of these displays, especially this one, for example, it's a lot of just like black empty space. And so we can do something cool with that. Maybe put the AXA logo right there, like that.
Yeah, we'll look into stickers. We might do like a 1/4-inch plaque or something like that. We'll see which is cheaper, and we'll let you know.
Do you want to consider that in terms of cost or?
No.
Okay. So just the base cost of what it would take to get a working display and everything.
Yep. Yeah, the base cost of everything, and then see if you can quickly get an estimate on like just some GrabCAD 1U CubeSat 3D printed. See if you can get a cost estimate on that. They normally take half a day to get those quoted, and see if it's like, you know, might be $20 or something like that. And add that in as well. All right. Thank you, Reese.